This is the introductory workshop, which will last through most of the day. I'm Ed Crawley. I'm going to give the first session, which is a little bit of an overview and talk specifically about the first two of the standards or principles of effective practice. And then I'll be followed by speakers who will speak to many of the remaining. And then we'll conclude at the end of the day with a workshop on implementing CDIO in your home institution. So the objectives of the workshop, as you can see here, are to explain the CDIO approach, determine ideas and ways in which it can be adapted to your home programs, but also to share your ideas and experiences. Now, this is quite a large group, so this will be somewhat difficult to do, and we will break down into smaller groups for some discussions. But we recognize that everybody who is here, especially at this meeting, is totally committed to improving engineering education. That's why you're here. So it's not like we have all the answers. One of the things we try to do at CDIO is just to create a framework in which discussion and sharing of ideas can take place. So we want to recognize that at the very beginning. So within the sort of system of an education, we're starting up at the top with the introduction, and there are various questions and topics that you have to address that are loosely shown here. Why do we prepare engineers? The CDIO is the context. What should students learn? The syllabus. And then how, which is the remaining topics, by designing good curricula, by focusing on learning, in particular for engineering students to focus on design implement experiences, and then to consider implementation so that the program is successfully put into place and is sustainable. And this roughly is the flow of today's workshop. I'll talk about the first two boxes at the top. CDIO is the context and the CDIO syllabus. And then let me, Christina, help me remember. You're going to talk about integrated curriculum with Johan Malmquist. And then Andrew is talking about active learning. And then Jakob and Johan, and you are talking about design implement experiences. And then I'll come back with a large group to talk about implementation. So that's the introduction to the workshop. Now we'll go into the first topic, which is establishing the context and defining learning outcomes, which are the two yellow boxes there. So the objectives of this particular session now, this first of the five, are to explain CDIO as the context, the CDIO context as an approach, to describe the content and structure of the syllabus, and learn how to engage stakeholders in the validation of the program objectives. So this is really the chart on which the CDIO program begins. And as I said, I can actually shorten up my comments today because some of these I realized were actually in my overview talk of just an hour ago. There was, by the early 1990s, throughout the world, a recognition by the people who hire our students that our students had changed. Now, this means between about 1960 and about 1990 they had changed. And the underlying cause we'll discuss in a minute, but the response of industry was almost exactly like the response of industry you heard this morning from the Lego guy. They want students with certain combinations of attitudes and skills and knowledge. And the most convenient way they can do this is to make a list. You see, so this guy actually did a fairly clever job. He said, well, conceiving, designing, implementing, and operating, we need that, but we also need collaboration, someone help me, dedication, innovation, and optimism, right? You see, so this is actually very good because what he reproduced is some of the other parts of the CDIO syllabus. You see, collaboration is section 3.1, teamwork, we called it. Collaboration, teamwork, they're different names for the same thing. Dedication is one of the attitudes that's in the CDIO syllabus, section 2.4. But he's not an educator. He just understands the needs his company has, and he made a list. We'd like students with all these things. And there's actually dozens of these lists. And I just put up a representative one on the left-hand side, which is no one's in particular, but is just typical at what industry says. We need students who understand the fundamentals, but also understand the design and manufacturing process. He said CDIO. A multidisciplinary system, good communications, he said collaboration, high ethical standards, and so forth. And this really wasn't getting much traction. This set of lists, when they were presented to university faculty, had more or less exactly the reaction that Johan Malmquist talked about a half an hour ago, and he said, well, the normal reaction of university professors is, this is good, but this is what they'll learn in industry. I can teach them mathematics. Right? And that's sort of where the conversation ended. So we decided to try to pose the question in a different way, to pose the issue in a different way, which is on the right, to try and make our colleagues understand what we call this underlying need, that we need to educate students who can conceive, design, implement, operate value-added engineering products in a modern team-based environment. And most of our colleagues will read that and recognize it as something that we should be doing. And then they'll start to ask, well, are we doing it effectively? How could we do it? And of course, the need to do this is what generates this list. To work in a multidisciplinary, team-based environment, you need to be able to collaborate and communicate and so forth. So this phrase, conceive, design, implement, and operate, which is meant to talk about, to describe the life cycle of an engineering product or process or system or software or molecule or material, that's where the name CDIO, conceive, design, implement, and operate, that we focus on the product or process or system life cycle. So the fundamental observation is that this is the context of the education, not the content. We'll still teach mechanical engineering, nuclear engineering, IT, but the context is that we'll teach it in with this idea that what engineers do is go and design and build things. Now, it's worth noting why we're all in this situation. And with a few exceptions, and I would say the Grandes Écoles in France are an exception, some of the German universities are an exception, but with few exceptions, this describes the evolution of engineering education over the last half century, is that it was in the 1950s and 60s an education based on practice. The professors of engineering were distinguished practitioners of engineering who had come back to the university to teach. And in fact, I went and looked at the faculty of my department, Aeronautics and Astronautics, in 1945, and not a single member of the faculty had a PhD. In fact, PhDs in engineering were very rare in 1945. So what happened is that in the 1950s and 60s, this new model of engineering education based on engineering science was introduced. This was a new idea, and it displaced the old idea of engineering practice almost completely. So that by the 1980s or so, engineering educations around the world had become very theoretical. And that's when, around the world, the companies started to react and say, these students are basically not able to be effective engineers. A very similar thing, by the way, happened in medical education. It was a practice-based education. It became a very science-based education. And the older doctors reported that the young doctors didn't know how to be a doctor. They knew about medical science. And they went and reformed medical education to return it to a basis of practice as well. So what we've done is we've moved sort of away from teaching students the personal, interpersonal, and system building skills and towards teaching them the increasing amount of disciplinary knowledge. But the students need both. So we can't just reverse the trend. We can't just say, well, we'll teach them less knowledge and more practice. What we have to do is we have to move off the frontier. We have to find ways that we can teach the students in the allotted time both the skills and the knowledge. And luckily, we're in an era where there's a great deal of work that's been done on learning that helps us to do this. So the basic idea of CDIO is to take what we now know about learning, and specifically engineering learning, and allow us to do better. So here are the goals. Second time you've seen them today. See if you can notice the difference. To master a deeper working knowledge of the technical fundamentals, lead in the creation and operation of new products and systems, and understand the importance and strategic impact of research on society. So you'll notice in the first one it says deeper working knowledge of the fundamentals. It's not just surface knowledge. We actually want the students to understand the concepts, to be able to apply them more effectively, to understand how they link together, as well as teaching them to lead in the creation and operation of new products, processes, and systems. So the vision that we have is fairly simple, stresses the fundamentals. Notice that we always say that first. The first reaction of most of our colleagues to this is you're going to dumb down the education. You're going to dilute the education in the skills, in the knowledge. Nothing is farther from the truth. Okay? It's all focused on understanding the learning of the student of the knowledge and how we can best bring that about. So set in the context of conceiving, dynasty, and implementing. So these are sort of the main points. A curriculum organized around disciplines, but disciplines that are explained to the students as interacting and supporting, not stovepipes of disciplines. With the skills interwoven, that is to say, the integrated curriculum. The skills appear within the disciplines. The design implement experiences set in both classrooms and modern learning workspaces, active learning, active and experiential learning, and a comprehensive assessment and evaluation process. Now, it is not a coincidence that the agenda for today is that I talk about the big print, and then Christina talks about the curriculum, and then Jakob talks about the design implement experiences, and Andrew is going to talk about active learning. That these are sort of the principal parts of the vision. And in fact, this chart was made long before the workshop was designed. So one of the things that, if you're not familiar with the literature on engineering learning, that we try in CDIO to form a bridge from the classroom teacher to the scholars on engineering education. And there's quite an active and growing community of these people. So I'll try and point out just some of these bridges. The first is, as I'll come back to in a few minutes, learning in context. Students learn better if education is set in an authentic context. If they're surrounded by people who are doing something real, they understand why it is that they need to learn what they're learning. Therefore, set the education in an engineering context. Learning styles. Most engineers tend to learn from the concrete to the abstract. Right? So it means if you ask a student in, say, their second or third year, did they understand the mathematics of calculus better if they learned the physics first? Or did they understand the physics better if they learned the mathematics first? Most of our students will say they understood the mathematics better if they learned the physics first. So they've learned the more concrete thing, which is mechanics of a rigid body, and then that helped them understand the mathematics that describes the mechanics of a rigid body. But how have we designed our curriculum? We've designed our curriculum to have a layer of abstraction called science and mathematics, and then another layer of abstractions called engineering fundamentals or engineering mechanics. And then only at the end, in a conventional way, if ever, do we expose our students to the concrete. Here is how you actually design a bridge, a piece of software, a new molecule. Right? So we have to actually map and adapt the way we design curricula to the way our students learn, not the way we think. See, we are experts. As through a progression of learning, it's a great story, I'll tell you. A progression of learning, it's identifiable. There's 4 stages. Not knowing what you don't know. That's the first stage. That's our students when they arrive at university, right? They don't even know what they don't know. And then as you begin to study something, you start to learn about how much there is to learn. That's called knowing what you don't know. Hopefully, by the time a student becomes a graduate of a 4 or 5 year program or a graduate student, they know what they know. We are not any of those. We're experts. We don't know what we know. We have so much knowledge, and it is such a part of our way of thinking that we've forgotten how we learned it and how hard it was to learn. And we've built an organization of that knowledge in our brains that is characteristic of an expert, right? But the way an expert like us thinks about knowledge is not the same way that a struggling 19-year-old student who doesn't know what they don't know learns the knowledge. So as we think about these issues, we have to think back, or we have to engage students, real students, to help them remind us how it is that they think about the knowledge. Last, a very related point is learning organization. As experts, we actually have in our mind a structure of the knowledge. Knowledge consists both of facts and theories and theorems and data and the way we connect it. And we have in our education lots of places to teach students the facts and the theory and the theorems. And where are the places we teach them how to connect it? Because actually making the connections between the different pieces of knowledge is actually one of the most important things. So in CDIO, one of the things we do is we use the design implement experiences to help the students make these connections, to do this scaffolding of different types of knowledge and connect it together. So what we try to do in CDIO, in the CDIO approach, is to create these learning activities that have this dual impact, that they teach the students about the technical knowledge, but also about the skills at the same time. And that gives us the possibility of teaching the students, of having the students learn more in the time they're allotted. Okay, so now I'll get to the first of the principles of effective practice, the learning context. So context, as I said earlier, is not a word that translates very easily. So the meaning is the words or phrases or passages that come before or after a particular word to help explain its full meaning, or the circumstances or events that form the environment within which something takes place. So a learning context refers to the circumstances and surroundings around the learning that help the students to understand meaning. So what's the context of engineering? Does this picture look familiar? What's the context of engineering? Well, it's the life cycle of a product. It's conceiving, framing the question or the problem, understanding the need, the technology, creating the solution concepts. It's designing, creating the information artifact that's necessary for implementation. Implementing, actually building something. Operating. The context of engineering, the authentic context of engineering, is not research. Very few of our students go off and do research. Most of them go off and work as engineers, even at MIT. Only 10% of our graduating undergraduate students go off and do anything that looks anything like research. So we have to build this context around them. And if we do that, if we set the education in the context of real authentic activity, it provides the benefits of contextual learning. It increases retention, that is to say the students remember things better. It allows them to build this kind of structure and interconnection, and it communicates the rationale for the learning. So let me tell you a little anecdote. I have a colleague who teaches a first-year subject. It's an optional exploratory subject on microfluidics. Okay, very hard to teach to first-year students. So he had this group of 30 students, and he taught a few classes, and by 2 or 3 classes, he only had 20 students left in the room. The rest had dropped the course. So he said to the students, why did 10 students drop this course? They looked at him and said, Professor, you haven't explained to us why this knowledge is important. See, we're experts. We know it's important. They don't know it's important. They don't know how it will be used or what it's good for. So he canceled the next class. He took them to a nearby hospital, to a laboratory where they did blood analysis, where there was all types of microfluidics. And he showed them how microfluidics were helping diagnose patients and test patients and preserve the health of patients. And he didn't lose another student the rest of the semester, because he had put the education in microfluidics in the context of human health. And that's all it took, one class. Do we take that class? Do we bring in one speaker when we're teaching aerodynamics to explain why aerodynamics is important? That's building context. So there's a standard, a principle of effective practice called, number 1, the context, which is the adoption of the principle that the product, process, system, lifecycle development and deployment, sometimes known as conceiving, designing, implementing, and operating, is the context for engineering education. It's what engineers do. It provides the framework for teaching skills, allows deeper learning, and, by the way, I think it does help attract and motivate students. And many of us are trying to attract and motivate and retain our students. So what I'd like you to do is to take a few minutes to turn to a neighbor in groups of 2s or 3s, and if there's someone who's not from your university, or if there's someone from university sitting next to you, turn the other way, and to discuss these questions. Just take a few minutes to discuss in what way you're improving the educational programs at your university, and in particular, what's the context of the education in which you teach. Okay? So we'll spend about 5 minutes. Just turn to a neighbor and get to know each other. Are you neighbors? Well, okay. One of the things we hope you'll do at CDIO meetings is spend lots of time meeting other people and exchanging ideas deeply. And we'll be doing this over and over through the day. But I did want to call in a few reports. There's 2 guys in the back who I asked if they were at the meeting or at the bar. And would you tell me what you said? Just speak as loudly as you can. Right. Why is the knowledge important? It's a you expect you're going to spend the next 15 weeks learning it. You should spend a little time talking about the answer to that question. We also had 2 professors from DTU from different departments that I found. And I said, well, that's okay because professors from different departments never talk to each other. And they said, no, we're actually married, so. So I won't comment about whether that means you talk to each other or not. But so now we'll shift to what we teach students. And as I've already said today, there's this underlying need to educate students who can conceive, design, implement, operate value-added engineering systems in a complex environment, complex team environment. But it's a university, so we also want them to be mature and thoughtful individuals, to broadly educate them. So in analyzing this and developing this taxonomy, which becomes known as the CDIO syllabus, we identified these 4 high-level types of knowledge and skills and learning. The first is technical or disciplinary, and that helps you build the product. The second is personal, that helps you understand yourself and be a whole individual. The third is team, or as the Lego guy said, collaborative, helping you work with others, communication, teamwork. And the fourth is understanding the process of conceiving, designing, implementing, and operating, the professional experience. And by the way, the CDIO syllabus says that you should conceive, design, implement, and operate within an enterprise, so that's the commercial business that he talked about, within a larger natural, social, and environmental context. So it seems that at the high level, there are about 4 sections to the type of knowledge that we can expect our students to learn. So what we did is we went a layer down from there and said, what type of knowledge specifically under these do we expect? And under section 1, technical knowledge and reasoning, this is really a placeholder. This is what professors always argue about. If you're a professor of computer science, this is your list. Do they need to know about databases? Do they need to know about data structures? Do they need to know about machine operations and so forth? If you're a civil engineer, it's do you need to know about soils, and do you need to know about structures, and so forth. So since we spend all our time arguing about that, in the CDIO syllabus we just made a placeholder, and we spent our time looking at the other 3. The personal and professional skills are the types of thinking that engineers commonly employ. Analytical reasoning, engineering reasoning, problem solving, experimentation, inquiry, discovery, system thinking. And then in personal skills and attributes, there's values and critical thinking, creative thinking. In professional skills and responsibilities, there's things like ethics and engineering responsibility. In the next section, there's teamwork, communications, and communication in foreign languages. And then lastly, there's conceiving, designing, implementing, and operating within an enterprise, within an external and societal context. This is about 17 topics, and this is the level at which most national accreditation systems look at engineering programs. And you can think about your national system. Everyone is different. But many of them now have outcomes, and many of them have a list of about 12 to 15 outcomes, and it's more or less this list. This list is more comprehensive than any of the national systems that we've encountered because we keep updating this list. But this is sufficient to set broad, high-level goals, but it isn't sufficient to actually design curriculum and exchange ideas. So in order to take care of that, we actually did the document at a 3rd level, and then at an even more detailed 4th, in some cases 5th level. And you can't read this, but you can turn to page 17, I think it is. 15 in the handout. And you'll see this at this 3rd level, so you can follow along. And I'll just take one. system thinking, thinking holistically, thinking broadly about all the issues that might impact you, understanding interactions in systems and resulting emergence, understanding how to prioritize and focus the issue on the appropriate issues, and understanding how to make trade-offs, judgment, and balance in resolution. So that's an outline of system thinking. And then in the full syllabus, there's one more level of detail that explains what each of those terms and topics mean. So that's the level at which you could actually design an education. Or if you said to a professor, would you be willing to incorporate system thinking into your subject on thermodynamics? And the professor said, I'd be happy to. What's system thinking? You could actually begin with a description of the topics in system thinking. So this is at the third level. As I said, there are about one or two more levels of detail. And it's rational. As a human, you can look at this list and you can sort of understand the structure. It's comprehensive in the sense that it's included all other references that we've encountered. It's peer-reviewed. That is to say, the section on communication was reviewed by communication experts so that it uses terms that people who teach communication would recognize. And it's, as I said, the basis of design and experimentation. So one other thing that became obvious within the last few years, although it should have been obvious when we drafted this in early 2000, is that these four bins, these four sections at the top, map very closely to UNESCO's 4 pillars of learning, which are learning to know, which is section 1, learning to be, ways of thought and attitudes and values, section 2, learning to work with others, section 3, and learning to do, that is to say, what does the profession that you're engaged with expect you to do? So it's interesting that independently we and UNESCO came up with these four high-level topical areas quite independently. And I find when I explain this to people, especially my colleagues, if I show them a list of 15 topics like in the national US accreditation system, ABET, they don't understand that list. But if I give them these 4 high-level topics and then the next level down, like this shows, and then I explain each one of them to them in some detail, they say, this is a reasonable list of things. Then of course, they say, how can we possibly teach the students this? But at least they understand what we're trying to do. So it's important to engage the stakeholders in setting the level of outcome of how well you expect the students to learn each of these things, right? So there's actually the second standard, which I'll show in a few minutes, which says that a program should set learning outcomes in each of these topics consistent with stakeholder input and program objectives or something like that. So the stakeholders are students, graduates of the program, people who hire graduates of the program, the professors who teach in the program, the university administration. It's important that you all agree. And what we have developed is a set of techniques, and you can see some lists here, that allow us to engage with the stakeholders, say, what are the more important things and what are the less important things for the mechanical engineering design program at Chalmers University? You have to actually make it that specific, because every one of our universities plays a slightly different role in society. So sometimes you can do interviews, you can have groups, focus groups discuss, you can do surveys, peer reviews, workshops. There are many different ways to engage the stakeholders, but it's important to do it. What we did at MIT and about a dozen other of the early CDIO programs, we did a survey process. And we asked this question: for each attribute, please indicate which of the 5 levels of proficiency you desire in a graduating engineering student. And then we created this 5-point scale. Have been exposed to be able to participate, to be able to understand and explain, to be skilled in the practice, or to be able to lead and innovate. And we took this survey data over many different segments, 25-year-old graduates, 35-year-old graduates, professors, people from industry, and we found a remarkable observation. I wouldn't call it a fact, but it's now been tested many times, is that when you ask these questions very clearly and very specifically, you have very broad agreement. So these 4 bars represent the answers on this 1, 2, 3, 4, 5 scale at my program, the Aerospace Engineering program at MIT, for graduating bachelor students. And you can see the 4 bars: blue is faculty, red is people from industry, yellow is 25-year-old graduates, and blue, light blue, is older, 35-year-old graduates. And look at how similar the mean of the responses is. That there is actually broad agreement as to what it's more important to have the students learn and less important to have the students learn. And in all of the universities that I'm aware of that have done this exercise, they reproduce more or less this pattern, which is that the different stakeholder groups actually agree. This was totally unexpected. What we expected is the industry would say one thing and the professors would say something else. And when we actually posed the question clearly and well, there was broad agreement. There's also relatively good agreement between institutions. This happens to be a comparison of a program in aerospace engineering, which is a 4-year program in the United States, and a program in mechanical engineering, which is a 5-year program in the UK at Queen's Belfast. And you can see reasonable agreement. The things that are more important always tend to be more important. For example, engineering, reasoning, and problem solving. And the things that are less important, like the enterprise and business context, tend to be less important consistently. For example, enterprise and business context. The top 2 or 3 always tend to be design, communication, engineering, reasoning, and problem solving, those few. So it's important to develop your own version of the CDIO syllabus. There's nothing, by the way, in any of the CDIO materials that's obligatory. You're not required to do any of this. These are resources. You can take any of these documents and adapt them any way you want. The principle is that you should set learning outcomes that are validated by stakeholders. And any way you want to do that is fine. But we provide documents and templates and so forth to help. So this is the second standard. This is the second effective practice, which is that specific detailed learning outcomes for personal and interpersonal product, process, and system building skills, as well as disciplinary knowledge, should be set consistent with program goals and validated by program stakeholders. So I want to do one other exercise. I'd like you, this one you do by yourself, I'd like you to take this page, page 15, okay, and for each section starting at 2.1, so for 2.1, 2.2, 2.3, 2.4, 2.5, and so on, I'd like you to rate yourself on this 5-point scale. In other words, engineering, reasoning, and problem solving. Have I experienced and been exposed to this? Am I able to participate in it? Am I able to understand and explain it? Am I skilled in the practice and implementation? Or am I able to lead and innovate? Then you answer the question about yourself about 2.2. And you can just take a pencil or pen and write on this piece of paper. So go ahead and take about 5 minutes to do that. And there's a few more that have arrived just in time if you didn't have one. But I would encourage you to finish it sometime today. But let me ask you, from amongst the questions that you answered, how many people gave themselves 1 or more 5s? Put up your hand if you gave yourself 1 or more 5s. Now keep your hand up. How many people gave yourself 2 or more 5s? How many people gave 3 or more 5s? 4 or more 5s. Yeah. So this is a typical result. On average, university professors only give themselves about 2 categories of a 5. Except in Northern Ireland, where one guy gave himself 14 5s, but he was an entrepreneur. So this is a lesson, you see, and I bet as I walked around, I saw many 2s and 3s, that we're experts, and we only gave ourselves a few 5s. So when you set learning outcomes for our students, you have to be very realistic about what level of proficiency the students can reach in 4 or 5 years in our programs. Okay, so that's the main points that I was trying to cover today. How can we do better? We can do better at making sure the students learn these things by retasking the curriculum, the teaching and learning methods, and so forth, which are the topics of the rest of the workshop and which are enshrined in the standards. So with that, I'll turn you over to Christina, who's going to talk a little bit about curriculum design. Are you going to use this or are you going to?
Yeah.